All right. Okay, so yeah, I go with the WebWorks due date. Yeah, yeah. Go with the WebWorks due date, right? Because all the grades in there, I end up just downloading and putting in Blackboard. Because apparently, that when we change the due dates in WebWorks, it doesn't change them in Blackboard. Okay, yeah, go with WebWorks due date. And all right, so last time well, first off, if you can remember these three identities, you can derive all the rest in one or two steps, right? I know there's like a million of them, but remember we used these to get our sum and difference last time. Like if we just take this guy, okay, and we take, say, the positive, the sum, and then we take the difference. And if you add these together, right, notice those go away and you get cosine alpha plus beta minus cosine alpha minus beta, gives you twice cosine alpha, cosine beta, and then you divide both sides by 2. Boom, you have product to sum, right? And you can do the same thing for all the different products, whether you want sine, sine, cosine, cosine, or sine, cosine. It's the same trick, okay? And there we go. You end up with, where are they? They're in here somewhere. There they are. So that's how you derive these four. It's the same trick for each of them, okay? So these give you your product to a sum, all right? Well, if we have product to sum, we also want sum to product, okay? Well, to do a sum to product, that's all that is your product to sum, but going the other way, right? If I put the 2 back over here, right? If I call this X and call that angle Y, all I'm doing is renaming my alphas and betas. Does that make sense? Right? If I'm like alpha minus beta is X and alpha plus beta is Y, if I add these together, I have 2 alpha is that, and then, okay, so if I call this angle X, then alpha here becomes all this, okay? So we just rename the angles, and at that point, uh, we don't want to use X's and Y's, you can call them alphas and betas. And you get the sum to product, which are here. Again, this is exactly the same as these. I'll put them all up here. So we have them all in one place. So I know they're kind of squished, but these are exactly the same formulas. I just moved the 2 over and renamed the angles. So you get a sum or difference to a product. So this section is just basically plugging and chugging, right? So we'll do one here. Let's see. Let's say I want to turn this sum into a product. This is useful in calculus. All right, so it's a sine of an angle plus a sine of an angle. So I go to my identities. I'm never going to remember all these, right? So I'll use this one. They have sine alpha plus sine beta is 2, sine alpha plus beta over 2, cosine of alpha minus beta over 2. I'll copy that. So we go to our formulas, find the one that we want, and we just plug and chug. So sine of 3 theta plus sine of theta going to be twice sine. We add our angles, divide by 2, and cosine, and then subtract our angles and divide by 2. Just following the formula here. Right? Is that okay so far? So we get 2 sine of 4 theta over 2, cosine of 2 theta over 2. And of course, we can simplify these, right? 4 over 2 is 2, and then cosine. That's all they're asking you to do. So I'm not going to cover this section too much because all you're doing is following the formula exactly. Y'all can do that by now, right? Right, here's your 4 formulas, or 8 formulas. They're all product to sum to product. You can plug in the numbers and get the results. So I don't want to waste a lot of time here because what we want to know, we could do this one. Let's do this one. This one looks good. Eventually, what we want to be able to do, like we do in all math classes, is solve for x, right? We haven't done that yet, right? That's what we want to do. So let's look at this. We have all kinds of different angles, right? Over here, there's just t. Over here, we have 2 t's and 4 t's. We could try using our double angle identities, right? If I wasn't in this section of the book where they just presented the sum and difference, I probably wouldn't think to use them. I would probably start using double angles to try to get rid of these, or half angles to try to get rid of the 2 t's and the 4 t's in favor of t, right? And that would eventually work. But if we realize what section we're in, we can go, well, this is a difference and this is a sum. Let's look at our 2 formulas. So where are they? Do this. So using this, let's see my left-hand side, right? I got a cosine minus cosine, so that's this one here. Let's rewrite the top. That would be a -2 sine. Now, if I add the angles, divide by 2, and then I have sine, and I subtract the angles, 4 minus 2 is 2. And then I'll do the same thing on the bottom. I have a sine plus a sine, that's this one. So that would be a 2 sine, add the angles over 2, and then I have cosine, subtract the angles over 2. So now that we did that, let's get rid of this guy. We don't need him anymore. And the reason why we might be motivated to do that beyond the fact that this section is about sum to product is it would be nice to be able to reduce this. Like if we could cancel something out, it's hard to factor when stuff is added and subtracted, right? When stuff is multiplied together, we can just do that, right? You can't do that up here. You can't be like, oh, it can't be like that, because stuff is added. When everything's multiplied together, we can. So those go away, and we have negative sine t over cosine t, which is exactly negative tangent, right? So I'd rather work, like if I'm trying to solve for t, I'd rather work with this than this, right? Let's look at another identity here. Okay, here, using double angles. So now we're not even going to use the sum and difference. Over here, let's work with both sides of the equation at the same time. Here I have one pile of stuff. Over here I have 2 piles of stuff. I don't like that. Over here I have sines and cosines. Over here I have cosecants. Cosecant sucks, so let's get rid of it. Cosecant is 1 over sine squared, right? And over here, this has 2 theta. Everything else is just theta. So I'm going to get rid of that. I'm going to use my double angle. That would be cosine squared minus sine squared. So again, the motivations for doing that is cosecant sucks, right? And why have double angles and single angles? I'll just make everything single angles. It makes it easier to compare, right? I'm trying to make samesies here. So now my motivation for my next step is, this is one big pile of stuff, and here I have two piles of stuff. So how about I combine these by getting a common denominator? 2 would be 2 sine squared over sine squared, right? All right, so I did that just to get a common denominator so that on the left-hand side, I could write this like this. So now it's one pile of stuff versus one pile of stuff, right? Makes it easier to compare. They both have sine squared on the bottom, so I need to show that these are the same, right? I'll keep this. So this only has sines in it. This over here has sines and cosines. Well, I know that cosine squared plus sine squared is 1, right? My Pythagorean identity. So I can always replace cosine squared with 1 minus sine squared. And we're done because this is that. Everything else is the same. You'll follow the motivation for each step. We're trying to make samesies here, right? That's what you don't get out of the book. The book will just say, and then you use this identity and it equals this. And you can look at each step and go, yeah, okay, that does equal that, but it also equals an infinite number of other things. Why did you pick that thing, right? So there's your motivation for each step. Let's do one more here. All right, I'm looking at this. I see 3 trig functions on the left-hand side and only 1 on the right-hand side. So this one, instead of working with both sides, there's not a lot to work with on the right-hand side. So I'm going to take the approach of start with one side and then show it's equal to the other side. So 3 different trig functions, and none of them are sine. This says sine, right? So first thing I'm going to do is get rid of all the tangents and cotangents. One thing you should recognize right off the bat is that's just 1, right? Tangent is 1 over cotangent, right? Right? I could be like, not notice that and be like, okay, tangent is sine over cosine and cotangent is cosine over sine, right? And then I'd be like, okay, that's 1. And 1 minus cosine squared is sine squared, right? Because cosine squared plus sine squared is equal to 1. And we're done. And that's it for that section. Again, I sped through that section. I mean, we started it last time, but most of it was just plugging the numbers directly into the formula. I want to get to this section because it's much harder. All right, we want to be able to solve for x or theta or whatever they want to call it. Let's start off with a very simple example just to get some notation down. Solve for theta. Okay, here's my unit circle. I'm looking for angles where cosine is a half. Well, cosine is the x value, right? So I'm looking for, here's the line, x equals 1/2. So where cosine is a half, or cosine, we need this angle and this angle, right? Those are the angles where cosine is 1/2. Good so far, basic unit circle stuff. So I'd be like, okay, well, theta has to be either, what is this? This is pi over 3 or negative pi over 3, right? But I also want this angle and that angle and all the possibilities, right? So since cosine is 2 pi periodic, I would put here plus 2 pi k, where k is an integer. Remember, funky z means integers. That's 0, 1, 2, 3, 4, 5, -1, -2. All I'm saying is take this number and add or subtract any multiple of 2 pi to it, right? And I could do the same thing here. But why write this twice? Can't I just say plus or minus pi over 3 plus 2 pi k? That's much more concise, isn't it? Sometimes you can get away with that. Sometimes you can't, right? For cosines, you can't. Sines, you can't. But I just threw in a whole lot of new notation. It's kind of abstract, right? But that's how you would write down the infinite number of solutions to this equation. Y'all good with that? All right, you need to have that down before we can move on. So that's a simple example. Let's look at a sine one here. It could be just as simple, but the numbers don't come out as pretty. So here we're calling our variable t. So what? So where is sine a half? Well, sine is the y value. So let's see. Here's all the y values of a half. So I need this angle and that angle, right? That's where sine is a half. So I'd say, well, t could be this angle, which would be pi over 6, or this angle, which is 5 pi over 6, and then anything that points in the same direction, right? So here we kind of have to write two separate things just because of the symmetry. Right? Is that okay? All right. Sometimes they make it a little more difficult. Here it's not just sine or cosine. Well, what we're going to do is just rearrange it to where it's just like one of the last columns. 2 cosine theta. If I add 3 to both sides, I get this. If I divide both sides by 2, I get this. And so cosine is the x value. That's the only angle where the x value is -1. So theta has to be pi, or anything that points in the same direction. Here they say, we only want the ones between 0 and 2 pi. Okay, well, that's just going to be pi then, right? The negative pi isn't in there, right? 2 pi isn't in there, right? Because this is less than, strictly. It's not equal to, okay? So it's just pi. The book does like 7 or 8 really simple examples, and then they give you this super hard one. So I want to make sure that we can make it to the hard ones, you know, because that's what's going to be on the homework, right? So here, let's see. I need to rearrange this a little bit. This is the same thing as if I added 1 to both sides. Okay, divide both sides by 2. All right, take the square root of both sides. And if I rationalize this, I might recognize it like that. All right, these are equal. Again, the charts and everything, you know, the tables always have that. But when you actually do applied math, they always write it like this, because there's nothing wrong with this number, right? So just be aware you can recognize this. So if we look at our unit circle, where is sine is the y value. So here is y equals positive root 2 over 2. Here is y equals negative root 2 over 2. So we need that angle, this angle, this angle, and this angle, right? These are all diagonals. Well, how would I write down, excuse me, those angles? Well, I'd say pi over 4, right? And instead of putting each of these, I recognize the fact that from here to here, that's pi over 2. This is pi over 2, that's pi over 2, that's pi over 2. We have symmetry here. So if I just add every multiple of pi over 2, or subtract every multiple of pi over 2, I have all the solutions, right? Yeah. Right? So you don't always just throw 2 pi, right? You want to look at your circle there so you can write down your solutions. They only want the ones between 0 and 2 pi. So that would be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Well, that's when k here is 0, 1, 2, or 3, right? Because you're taking pi over 4 and either adding no multiples of pi over 2, 1 multiple of pi over 2, or you're adding 2 multiples of pi over 2, so on. Okay. So again, these are the easy ones. Here's some more easy ones. Cosecant. Cosecant sucks, so I replace it with 1 over sine, right? And if I take the reciprocal of both sides, I get this. So where's sine minus a half? Well, sine is a y value. There's y minus a half. So we need this angle and that angle, right? So let's see, what would these be? This would be 7 pi over 6. And then this would be pi over 6 short of 2 pi. So it would be 11 pi over 6. Right? 2 pi would be 12 pi over 6. I need one less than that. Then add 2 pi k. So when anything that points in those directions, there's all the solutions. They want the ones between 0 and 4 pi. Okay. I know I need 7 pi over 6, and I know I need my 11 pi over 6, right? So what are the other ones? Well, if I'm here, I just need to add 2 pi to each of those, right? Well, let's see, 2 pi is 12 pi over 6, right? So if I add 12 to 7, get that, all I did was add 2 pi. And then the same thing with this one, this 11 pi over 6. If I add 12 and 11, I get what, 23 pi over 6, right? So those are the 4 solutions between 0 and 4 pi. Here's all the solutions, right? Here we go, here's tangent. This one, this is a good example. It's simple, but if you have something in here other than just theta, right, it might think, oh, that's going to make things really hard, right? That's okay. It's really not. Just think of this as x, right? Theta is an angle, pi over 2 is an angle, theta minus pi over 2, it's still an angle. It's just numbers, right? It's a number with a longer name. So where is tangent equal to 1? Well, it's equal to 1 here and here, right? Which would be, so whatever it is in here, I don't care if it's theta squared plus 2 theta minus whatever it is, no matter what it is, I'm going to call it x. Whatever that stuff is in there, it has to either be pi over 4 or pi k. Remember, tangent's pi periodic. If I add pi or subtract pi, I'm going to get an angle that points in those directions, right? But that's what x is, right? Well, x, whatever that stuff is in here is really theta minus pi over 2. Okay, so all I did was replace that with what it is, because we don't want to know what x is, we want to know what theta is, right? So if I add pi over 2 to both sides, pi over 4 plus pi over 2 would be 3 pi over 4. So there's all the solutions, right? Of course, they only want the ones between 0 and 2 pi. Well, we could just look at it. Pi over 4 and 5 pi over 4, right? I want to make sure y'all can get all the solutions as well as just the 2 they're asking for, right? Because in the next section, they say solve for x, and they want all the solutions, okay? So you want to be able to do this stuff. If I'm going too fast, let me know, because I just finished my bang. Hey, let's do this one. This has a whole bunch of stuff in it. All right. So now there's tangents everywhere. That's no big deal, right? We can, right? Whenever you have something with x's everywhere, you consolidate your x's, right? Get them all together. So let's see. If I multiply this out, I got a 2 tangent x plus 6 equals 5 plus tangent. Well, I can subtract tangent from both sides, right? And I can subtract 6 from both sides. So this is easy, right? Where's tangent minus 1? Over here and over here, right? So x has to be, what, 3 pi over 4? And then add any multiple of pi, right? Add pi or subtract pi as many times as you want. So they want all the ones between 0 and 2 pi, though. So that would be 3 pi over 4 and 7 pi over 4. Those are the ones in the restricted zone. Not bad, right? Let's see what happens when they throw us something ugly here. Here's a good one. Use the calculator. Solve sine of theta equals 0.8. Okay, well here's my unit circle. Now, sine is the y value. 0.8 is pretty close to 1. It's somewhere up here, right? So how do I figure out what these angles are? Well, if I did theta equals sine inverse of 0.8, it's going to give me that number, right? Whatever number that is, your calculator is going to give you a number, right? But we also need this one. So that would be pi minus sine inverse of 0.8, right? And then, of course, we want anything that points in the same direction. Now, they say use a calculator. I don't want to waste my time with a calculator, so I'm just going to look and see what the number is. So that's what that number is. So replace this with 0.9273, right? I always leave things like that because then it's exact. It's an approximation. Okay? But for the WebWorks, they're going to want you to use your calculator and get an approximation. So you'll actually have to plug that number in. All right. But again, sine inverse is always going to give you an angle over here. It's always going to give you this one. It's not going to give you an infinite number of answers, right? Now, if you're using your laptop or something, you could just type in solve, and the real software would tell you all the answers. All right. Let's look at. I guess we could do this one. Not 4 and 4 and 2. Let's look at this one. All right, this is the hard one. So here they have cosine squares and cosines and stuff. What this thing looks like is x squared plus 3x minus 1, where x is cosine theta, right? Right? If you look at it that way, it looks like this, right? Y'all are used to solve, y'all know how to solve for x, right? So first off, forget that it's trig. Just solve for x. Solve for what cosine of theta is, because if you can turn this into cosine theta equals a number, right? Then you can solve this, right? So I might look at this and be like, it's like that. First step I want to do is factor it. If I tried to factor this, it'd be like cosine squared. I know I need a cosine and a cosine, and then I need two numbers that multiply to give me minus 1 and add to give me 3, right? Y'all remember basic factoring, right? They should have given a problem where you could factor it, but you can't. There are no, the only two numbers that multiply to give me minus 1 are minus 1 and 1, and they never add to give me a positive 3, right? So this is not factorable in that sense. So that didn't work. So what do you do when you have something like this and you can't factor it? How do you solve for x? What's the only other thing? You have the Pythagorean theorem, and what's the other thing that you've used? The quadratic formula, right? Those are basically your two things. That's all your math. Quadratic formula and Pythagorean theorem. So here, if I call this stuff x, right? So this didn't work, but if I call this stuff x, it's really that, right? So the cosine theta, which I called x, right, would be what? Negative b plus or minus the square root of b squared minus 4ac all over 2a, right? Which would be negative 3/2 plus or minus the square root of 9 plus 4 over 2, or negative 3/2 plus or minus the square root of 13 over 2. So what I have here is cosine theta, right? I solved for x, but x is cosine theta is equal to this pile of stuff, right? So I solved not for theta, but for cosine theta. Well, this is just a number, right? So what I would do is I'd say, okay, well, theta is cosine inverse of this stupid number here, whatever it is. It's just some decimal, right? Whatever that number is, cosine is going to give us an angle over here on the right-hand side, cosine inverse, okay? But we also have to recognize theta could be this one as well, right? So theta would be plus or minus that plus 2 pi k. Now the book wants you to use a calculator, right? So let's see what that number is. So this big stupid number, okay, if you take cosine inverse of it, it's 1.26. Okay, so let's draw our picture accurately, right? So I got a solve for cosine theta with the quadratic formula, and then I need to solve for theta. So I take cosine inverse of both sides. The calculator says 1.26. Well, pi is about 3, right? So 1.26 is somewhere over there as an angle, 1.26. All right. So we also need negative 1.26. So theta is either plus or minus, I should say, plus or minus 1.26 and any angle that points in the same direction. So this is the hard problem, right? The hardest part is the quadratic formula, which you all already know. So it's really not that hard, is it? It's just putting together everything you know, okay? So again, I guess it's abstract, right? But you see the form. This is the same form as that, right? So first solve for x, right? So we got x is this, but x is really cosine theta. From there, this is just a number, has a big ugly name, but it's just a number. You could plug that into your calculator if you wanted, but right. So theta, one of the solutions is when you take cosine inverse, and it gives you that one. You have to use your knowledge of trig to figure out, well, the calculator didn't give me that one, or this one, or this one, and so on. From there, they say, we only want the ones between 0 and 2 pi. So that would be 1.26 and 2 pi minus 1.26. Those are the ones between 0 and 2 pi. Is that okay? I know it's a lot. All right. Let's see. That's as far as I got in the last class. But we can look at another one. Let's do another one. Maybe this one will be factorable. Okay. Here, it's just another quadratic, right? This looks like 2x squared minus 5x plus 3 equals 0, where x is sine theta, right? That's what it looks like. Maybe this thing's factorable. May as well just use the quadratic formula, right? I don't want to see if it works out by factoring by grouping. Probably could, but just use the quadratic formula, it'll work. So x would be, and notice they already laid it out all nice. If these were all rearranged and stuff, y'all know your algebra. You try to turn it into something that looks like this, right? You know how to do that. So x would be negative b plus or minus the square root of b squared minus 4ac all over 2a. So this is 5/4 plus or minus 25 minus 4 times 2 is 8 times 3 is 24. This is 5/4 plus or minus 1/4. This is either 6/4 or 4/4. This is what, 3/2, and this is 1. All right, so we solve for x, but x is sine theta. So we have two of these here. We have sine theta equals 3/2 or sine theta equals 1, right? So this one gave us two different equations here, right? So sine theta is never equal to 3/2, right? Sine is always between -1 and 1. So this one doesn't have any solutions, right? This guy, when is sine theta equal to 1? Right there. The theta has to be pi over 2 or anything that points in the same direction. All right. Which reminds me, right? We have two solutions here, the plus and the minus. Let's go back to this one. I forgot there's two numbers here, right? So we need to do both of those, right? There's the one with the plus, and then there's the one with the minus, right? So we only got half of the solutions here, right? What about the one with the minus in there? All right. So see, there's one with the plus and one with the minus. So we really need this other one, cosine inverse of negative root 3 over 2 minus. So we need one with the plus and one with the minus. Gives you a whole nother set of solutions. Okay. So like this one, we got two equations, right? One of them didn't have any solutions. The other one gave us a few. Okay. Let me see why they don't have that one. So they have plus and minus, plus and minus. Only the plus sign is used because we get an error. So, okay, same issue up here. When you subtract there, this number is smaller than -1, right? So cosine is always between -1 and 1. So this one, this chokes, right? Because this number is less than -1. It's outside the unit circle. Okay, so that one didn't give us any solutions. That's why they only used the plus sign, because this number is between -1 and 1. Any questions? All right. Practice, practice. You can handle this. And I will see y'all Monday. Have a good weekend, everybody. Question about my grade. So on the